Welcome to the third and final part of this module. In this video, we will explore a technique that is both simple and incredibly powerful: the creation of spatial grids. These are regular spatial mesh that divide space into uniform cells. They are extremely useful for systematic analysis and spatial modeling. But why do we use spatial grids? In many cases, we need to analyze large territories, maybe an entire region or country, and break them down into comparable units. These allow us to perform evaluations cell by cell. For example, which cells are suitable for wind development, which are close to infrastructure, which have high demand density. Grid also remove administrative bias. Instead of working with provinces or municipalities, which vary in size and shape, we work with neutral, uniform size zones, enabling unbiased spatial statistics. Let's start with QGIS. Creating a grid here is simple and visual. Go to the menu, Vector, Research Tools, Create a Grid. You can specify the grid type, usually rectangle. Then choose the grid spacing, for example 5 x 5 kilometers. Set the extent, either manually or based on an existing layer, like the boundary of your study area. Then choose the CRS. Once created, you can intersect the grid with other layers. For example, calculate the average wind speed per cell, or identify which cells are within a certain distance of infrastructure. Now, let's switch to Python and create a grid using GeoPandas. First, we need to define the extent. This can be done by loading a polygon layer and computing its boundary box. Then we loop over that extent, creating rectangles cell by cell. Here's a simplified code snippet to build a grid of 5 km cells. Let's now look at 3 real-world applications of spatial grids in the energy domain. Infrastructure planning. Suppose you want to extend a medium voltage grid to undeserved areas. You can create a grid over a region, compute distance to nearest substation, and then use this to prioritize areas that are far from the network. Site suitability analysis. You want to map where wind turbines could be installed. For each cell, compute average wind speed, presence of constraints like protected areas, and proximity to grid. Then classify each cell as suitable, marginal, or excluded. If you plan hydrogen infrastructure, you can place candidate stations on a grid and model coverage radius to analyze which zones are served and which are gaps. Before closing, a few best practices when working with spatial grids. Always work in a projected CRS to ensure distances are in meters. Choose your cell size carefully. Too small and your processing time explodes. Too large and you lose resolution. Use aggregation functions carefully. Mean, max, count, depending on what you need. Grids are powerful. They allow scalable, structured spatial analysis from local to continental level. And they play a central role in energy system modeling, from resource assessment to infrastructure optimization. To recap, we learn how to create spatial grids in both QGIS and GeoPandas. We saw how to intersect the grids with other layers and compute spatial statistics. We explore real application in infrastructure planning and site suitability. In the next module, we will shift our focus from vector data to raster data, which is equally essential in energy planning. You will learn what raster datasets are, how they differ from vectors, and how to use them to estimate renewable energy potential across large areas. We will download the wind speed maps, load them into QGIS, and start performing real spatial analysis based on continuous environmental variables. See you in Module 3, Raster and Vectorial Analysis for Renewable Energy Planning.